Okay, good morning. So, in the previous lecture, we have started our discussion on experimental measurement of void fraction. Okay, so while starting the experimental techniques to measure the void fraction, we have to first get some mathematical idea that what are the measurements which we need to obtain in order to obtain the data of the void fraction. So in this we found that phase density function is one important parameter which is a function of position and time, and depending upon the contact or presence of a phase at a particular location at the given time, its value becomes either 1 or 0. So it's kind of an indicator function which indicates whether a phase is present or not. Once we have the data of phase density function available, then we can obtain this data for a larger interval of time, and corresponding to that, if we take the time average integral, then we will be actually getting the local void fraction at that particular location. And the selection of time step, how it is important in estimating the local void fraction, that we have seen that if our time period is very small, then we will be having oscillating pattern of the local void fraction, but if it is sufficiently large, then we will be getting almost a unique value. And other than that, we have also seen the indications of one-dimensional void fraction, two-dimensional and three-dimensional void fraction. So typically whenever we are referring along a line, we are calling it as 1D void fraction. If we are referring over a cross section, then 2D, and when we are considering the volumetric basis, then we are calling it as three-dimensional void fraction. Now, after this mathematical understanding, what we need to do, we need to devise some experimental ways so that we can obtain the data of phase density function. Okay, so there can be two ways. Either we can obtain any of the parameters directly, or we can obtain data of phase density function. So let us discuss some of the techniques. First technique which I have listed over here, it is radiation attenuation technique. Okay, so if you see the layout of this technique, this is a pipe and this is the thickness of the pipe. It means this is the solid portion of the pipe material. Okay, and in between the pipe we have actually multiple fluids flowing. So these white color patches can be considered as the fluid particles, and these fluid particles are actually present in the surrounding of another fluid medium. Okay, now here you can see what we have. We have a source and we have a detector. Okay, so what we are doing, from this source we are sending some signal, and then we are trying to detect this signal at the detector part. Okay, so whenever the signal will be starting from the source, with its full intensity it will not be reaching at the detector. There will be certain loss in the this particular signal. Why there will be loss? Because this signal will be actually interacting with the different mediums which are in its path. Okay, so let us consider that signal has emitted n naught number of particles at this particular location, okay, from the source. And now what I mentioned, that while these particles will be moving further, these will be actually interfering with the different mediums. Once these are interacting with the different mediums, some of these will be absorbed and diverted from its straight path, whereas only few of which will stay in the straight path which can reach the detector. Is this point clear? So what will happen, see, whenever a particle comes, we will be having some atom of other medium, and this particular atom will be having some electron flow. Once this will be coming in the zone of influence of this particular atom, this will be deflected or adsorbed. Okay, and in this way any particle which has come in its zone of influence, that will not be able to reach the detector. Okay, so that will be deviating from its path, and some remaining particle may then move further. So it means that whenever we are starting from a point, then whatever is the strength of the signal, that strength of the signal will be will be deteriorating once we are reaching the detector, depending upon the presence of phases present in between. Okay, so that can be given by this formulation, n equal to n naught into e power minus x by lambda. Okay, where n naught is the number of particles initially emitted from the source, n is number of particles detected at any distance x from the source, and lambda is one important parameter which is given as 1 by sigma n, where n is number of nuclei per unit volume. Okay, and sigma is the cross section of the interaction. So what I told you, that if some atom is present, then this atom will be interfering with this particle, okay, and then it will be absorbing. So it means the rate at which these particles are getting adsorbed or getting decreased, that will be depending upon the number of nuclei which are present in the volume. If number of nuclei are less, in that scenario the rate of decrease will be less, okay, and if more nuclei are present, then there are more chances of the interactions. So that's why the amount of attenuation of the signal will be more. So one, it will be depending upon number of nuclei. Second, it will be depending upon the cross section of the interaction. What it means, every nuclei which is presenting, it has certain zone of influence. Okay, if say this is my signal and nuclei is present over here, this nuclei can only interact with the particle which are in this particular circle. So if this is away from its zone of influence, then it will not be affecting this. But say if some particle is present over here, then this ray is coming in contact with the zone of the influence of that. Okay.
So, will it be affected by dispersed phase particles only or by both continuous?
By both.
So, what if there is a flow of air in a liquid? Let's say there is a flow of air in liquid in pipe, then there will be an abundance of water in the pipe, right?
Yes.
So, the strength of the radiation will be diminished significantly.
Yes.
Then what will be detected at the detector? Then?
That is what we are trying to see. Let us understand this. Okay, so later on what we do, if our strength of detector, the signal which is reached at the detector is very less, then we do again the multiplication of the signal, amplification of our signal also. Okay, so that we have to do after the detector in the more detailed one. So at the moment I am just giving you the fundamental idea. Once we will be going for practical implementation of this, in that scenario, if the strength of the signal reaching the detector is so small that it is not able to distinguish for the different situation, then the signal is of no use. Okay. So sigma is the cross section of the interaction. Is this one clear? Now these two factors are basically controlling the amount of adsorption or amount of attenuation in the signal, and typically the values of sigma and n, because we are specifically talking about one particular type of nuclei, therefore the value of n is a function of material of the fluid or the nature of its molecule. Okay, so now you can see that n is having formulation rho NaV Avogadro number divided by molecular mass. Okay, because this interaction length lambda will be something which will be specific for each and every particle. Is this point clear? If you have air molecule, then their interaction length may be less. If you have water molecule, its interaction length may be more. Okay, if you have polar molecule, it will be different. If you have non-polar molecule, it may be different. So depending upon the nature of the molecules present in a fluid medium or solid medium, this signal will be actually increasing or decreasing. Now let's try to see, this is our generic formula. Now when I have to apply this formula for this given situation, then what I will be having? Now let us consider that small w is the thickness of the pipe material. Okay, then what I will be getting, n naught has started from the source, but this n naught signal, while it will be moving along the straight path, at two places it will be experiencing W amount of thickness of the pipe material. So that's why whatever attenuation of the signal will be taking place in the pipe material, that can be given in terms of exponential of minus, because minus x by lambda, here x for the pipe material will be becoming W amount here, W amount here. So it will be becoming 2W divided by lambda. Okay. Other than that, if say the distribution is such that corresponding to this gas, overall situation is nothing but my epsilon is length of the gaseous phase divided by total length, means total length will be becoming internal diameter of the pipe. Is this point clear? So in that scenario, I can say that length of the gaseous portion can be written in terms of internal diameter of pipe times epsilon. Is this point clear? All are clear with this point? So if I say that, because what is one dimensional void fraction? One dimensional void fraction is nothing but the length of the gaseous portion divided by total length. Lg divided by total length is d, internal diameter of the pipe. So from here I can say that the length of the gaseous portion will be d into epsilon. All are clear with this point? So if length of gaseous portion is d into epsilon, then the attenuation which will take place in the gaseous medium, that will be equal to exponential of minus epsilon d divided by lambda g. Okay. And what will be the remaining portion? Remaining will be length of the liquid. So length of liquid will be exponential of minus 1 minus epsilon d divided by lambda. So this will be the actual strength of the signal at the detector, which is considering attenuation in the pipe material, in the gaseous medium, as well as in the, say, liquid medium. Okay. Now what we have to do, because see, if randomly you try to test this, every time you will be getting some signal, but you will not be having clear idea. So in order to get the clear idea, what we need to do? We need to calibrate this system. So how we will be calibrating the system? What we can do, first we can allow the pure flow of the gas into the pipe. So once we are allowing pure flow of the pure gas flow in the pipe, corresponding to that, what will be attenuation? Minus 2W by lambda W, because pipe material is remaining the same, but what we are changing, through the entire diameter we are allowing only gas to flow. So minus d by lambda g. So this will be the value of signal if I take pure gaseous phase. And similarly, if I take pure liquid phase, then this will be my strength of the signal. Okay. Now what I can do, these two I can take ratio with the arbitrary signal n, and if I do so, I will be getting the relation that epsilon is equal to ln of n divided by nl, where n is the arbitrary signal corresponding to void fraction of epsilon. Okay, and divided by ln of ng by n. All are clear with this point? So if you just do manipulation of algebraic manipulation of these three equations, you will be getting that epsilon is equal to natural log of n by nl divided by log of ng by nl, where n is an arbitrary signal corresponding to any given void fraction epsilon. Is this point clear? So it means that now if you have some arrangement which can supply the signal and one arrangement which can detect the signal for a pipe material, and once you have calibrated it with the pure gas and the pure liquid flow, then for any arbitrary signal n which is obtained at the detector, we will be able to predict the value of one dimensional void fraction. All are clear with this point? So from here what we are getting? We are only getting the one dimensional void fraction. Why one dimensional? Because this signal we are trying to trace along a straight line. All are clear with this point? Okay, so this can be the experimental configuration to obtain the one dimensional void fraction. Now let's try to see if I have to extend this, okay, if I have to extend this for the whole cross section, because one dimensional void fraction is of no use. Ultimately, what I will be obtaining from the one dimensional void fraction. Okay, so our aim should be to characterize void fraction at the entire cross section. So to do so, I can have different arrangement. I can take a linear source, and from this source I can again take a linear detector. If I send the signal like this, then at each and every length portion it will be able to give me the value of the void fraction. Is this one clear? Similar way, there can be another arrangement where source is such that this particular source can send the signal in the range of certain angle, and then at different angle, whatever rays are starting from the source, these are detected with the help of different detectors. Okay, so typically what is the configuration of the detector, that let us try to understand. What type of sources we can use? Typically the sources which are used in radiation attenuation techniques, these are gamma rays and X-rays. Okay, so device which can supply gamma rays, these are called as the gamma densitometer. And typically in comparison to the X-rays, the source of gamma rays, which is gamma densitometers, these are of large size. Why? Because gamma and X-rays are some rays which are actually harmful for the body. So that's why whenever we are using this type of systems, we need not to simply use the source, but we also have to have some shielding arrangement so that rays can only pass in certain direction, and these should not come from all the directions. Okay, so there should not be any leakage of the gamma rays or X-rays, otherwise these will be detrimental for the health of the human who is handling that particular device. So that's why around this source we have to provide some insulation so that there is not leakage of the gamma rays or X-rays. So typically the insulation thickness which we need to use, or insulating material which we need to use for gamma rays, that has to be larger in size, because of which the size of gamma densitometer is more in comparison to the source of X-rays. And another important point is sensitivity of the system. If sensitivity of the system is very high, then most of the interactions will be taking place in the flow itself. So this is what question you are asking. So if sensitivity is very high, then what will happen? Most of the interaction will take place in the flow itself, and we will be having very fewer particles left for detector, and instrument will be having low accuracy. Okay, so once your strength of the signal is, say, what is my void fraction data? It will be varying from 0 to 1. If it is varying from 0 to 1, say I am doing measurement at a step of 0.5, sorry, 0.1, then 0.1, 0.2. Likewise, I will be having different void fraction data. Now, corresponding to say 0 void fraction, one value of signal I am getting as 1, and corresponding to this I am getting 2. Here if I am getting 1, and here I am getting 4 in some other device. In some other arrangement I am getting here 1, here I am getting 10. Now can you tell me which one is more sensitive, which one is more accurate? Last one. Okay, so wherever we have large range of output signal available, corresponding to that, whenever I will be doing interpolation, I can get the void fraction data in fractions also below these numbers. Okay, almost a continuous variation of the void fraction. But if my signal strength is very small, say it is varying from 1 to 2 only, then corresponding to that, whatever interpolation I will be doing, I will be having so many chances of getting errors more in comparison to the actual signal output, and there will be inaccuracies in the measurement. Okay, is this one clear? So that's why whatever is our range of operation of the measurement, in that the variation of the signal should be significant. If variation of signal is significant, then we will be more accurately able to determine the data. Okay. So what is the point? The point is, if sensitivity is very high to, then what we will be having, interactions will take place in the flow. It means almost all the emitted particles will get absorbed within the flow itself. So once these are getting absorbed within the flow itself, we will be having very less particles left at the detector, and signal of the detector will be weak. Okay, so with weak signal, making judgment will be actually difficult, and we will be getting signal in very narrow range. Okay. So detector is a scintillator which is coupled with photomultiplier. Okay. So here you can see in the previous figure, this is the scintillator which gets the signal, and corresponding to this signal, it actually starts the flow of the electrons so that we can measure some current or voltage at the detector part. Okay. And after it has started the electron flow, we do have some arrangement over here, and this arrangement is actually called as photomultiplier. So what is the purpose of photomultiplier? If we are getting a weak strength signal, if directly we are measuring that signal, it can give us the very poor quality of the signal and inaccurate measurement. So in order to improve the strength of the signal, what we can do, we can use some amplifier which will be actually amplifying this signal, and we will be getting a finite amount of voltage difference at the exit of the photomultiplier. Is this point clear? So this is an electronics arrangement. At present we are not interested in electronics part, because that is of interest to people who will be having involvement in fabrication of the scintillator and the photomultipliers. Over here our interest as a people working in mechanical engineering or multi-phase flow systems, our interest is to use these systems for measurement of our void fraction or other parameters. Okay. So scintillator and photomultiplier arrangement have you seen? So now you can see here what I have written, PM tubes. So these PM tubes are nothing but photomultiplier tubes as the detectors along different orientations. Is this point clear? Now scintillators absorb radiation and these emit visible light by fluorescence, and once visible light will be actually falling on the photomultipliers. What are the photomultipliers? Which receives the visible light and produce the electric signal. Okay. And typically photomultipliers will be converting weak luminous pulses into the electrical signals. And photocathode and cascade of pairs of electrodes use at different potentials. So we have seen some arrangement in the previous figure. So how we can use the radiation attenuation techniques you have seen. Okay. Now let's talk about the another type of technique which is called as optical probe. Okay. So the advantage with radiation attenuation technique was that it did not require any optical access to the pipe. Okay, because we were not directly dealing with the light, we were dealing with the gamma rays and X-rays which can penetrate through the opaque pipe material. But whenever we will be dealing with the optical probe measurement, then we have to use the material of the probe. If say I am putting the probe within the pipe, then material of the probe should be transparent. Okay, and if I am using probe from outside of the pipe material, then pipe material should be actually transparent, because we are now dealing with the optical signals. So once we are dealing with the optical signals, these should be transparent to the light. So is this point clear? Now in case of optical instrument, it is essentially based on the principle of behavior of electromagnetic waves at the interface of the two media. We know that whenever a wave is incident on an interface, then depending upon the characteristics, part of it is reflected and part of it is transmitted. Okay, so let's try to understand. say this is my typical interface, and in this interface I have two fluids. Bottom side is fluid 1 and the top one is fluid 2. Bottom is having refractive index of N1 and top one is having refractive index of N2. Now this is a wave of strength KL and it is having angle of incident theta I. Once it is incident at this interface, part of it will be reflected with strength Kr at an angle of reflection theta R, and part of it has transmitted with strength Kt at an angle of theta T. Is this one clear? Now, from our basic understanding of the optics, we know that theta incident will be equal to theta reflection and n1 sine theta I has to be equal to n2 into sine theta t. So this is coming from the basic laws of optics. Okay, incident angle will be equal to reflection angle and n1 refractive index of fluid 1 into angle of incident has to be equal to refractive index of fluid 2 multiplied by sine of angle of refraction. Okay, now let's consider that sorry, no, they are in different medium. This is N1, this is N2. So this is the interface between the two fluids. Okay. Now Rp and Rn can be taken as the strength of the signal, strength of reflected signal, which is parallel to the angle, parallel to the incident ray divided by original strength of the signal. Okay, this is Rp and Rn is the strength of the signal normal to the direction of Rp, normal to the direction of incident ray divided by original signal. Is this point clear? What is Rp and Rn? So if this is my incident ray, okay, of course incident ray will be having some reflection and some refraction. But if I consider that I am using source from here and detector I am using only in the direction perpendicular along the incident ray. Okay, so if my detector is here, then detector will be detecting the part of the signal which is available in this direction. All are clear with this point? So part of signal which is available in this direction, that is given by the value Rp, and part of signal which is available in direction normal to the incident ray, that is given by direction Rn. Is this point clear? So let us not go into the derivation of these at the moment. You just remember that these formulations are given to you. Now how we will be utilizing these formulations to obtain our data, that let us try to see. Now there is one interesting point. If I consider different angle of incidence, then corresponding to different angle of incident, if I plot the value of Rp and Rn from these formulations, I will be finding that up to some critical angle of incidence, value of Rp and Rn will be different and its value will also be small in magnitude. But after the angle of incidence crosses this critical limit, then the value of Rp and Rn will become unique. Moreover, its strength will also be significant. All are clear with this point? So, and particularly this graph is given when N1 is 1.6 and N2 is 1. So, this graph gives us one important idea, and typically you can also see the N1 equal to 1.6 is refractive index of glass and N2 equal to 1 is refractive index of air. So it means this graph is given for the combination of a glass tube and the air medium. So interface between glass and air. Now you can see one important observation. If I maintain my angle of incidence in the optical system which I am actually going to design or going to use greater than the critical value, then corresponding to that the strength of signal in parallel to the incident wave and normal direction to the incident wave will be same. At the same point of time, it will also be having the higher magnitude in comparison to the lesser angle. Okay, so this type of information is very useful, because now if you have any distortion in placement of the detector, that will also be accounted for, because both the strength of the signals is actually same, and at the same point of time you will be getting a strong signal at the output in comparison to a weak signal which was observed for angle of incident less than critical limit. Okay, so it means that this graph will be giving you the idea for different combination of n1 and n2, whatever we are using. We can plot this graph and then we can get the idea of critical angle of incidence. And whenever we will be operating the system, we have to keep our angle. In order to get a good quality signal, high strength signal, we have to always keep angle of incidence greater than the critical limit. Is this one clear? Now second thing is, whenever I will be using the optical probe, say one material I have frozen, I am using glass. Okay, because I have to use a transparent material in order to use the optical probe. So one material is glass, but when this glass optical probe will be interacting with the flow, in the flow other material can be any. Once it is interacting with the air, the material will be having refractive index equal to 1. If it is interacting with water, then refractive index may be close to 1.33. If it is interacting with some other type of liquid material, then refractive index can be different. For example, if it is interacting with kerosene, then it will be, I think, 1.6 or 1.4, something like that. So one material, our N1 is frozen if I am making the optical probe of glass material, but the other material which will be interacting with the probe, that will be subjected to our application. Okay, so that's why we have to also see the behavior of this one for different values of N2. All are clear with this point? So what I have done, I have plotted N2 along abscissa and incidence angle along ordinate, and corresponding to this we obtain a contour map where below these lines, so this is a spectrum of values, like below this line our RP is less than 0.2, so it means this line is corresponding to 0.2 and this zone is corresponding to RP equal to 1, and here RP will be less than 1. So this band is for 0.2 to 1, and above this everywhere RP value will be 1. So what is our requirement? Whenever we are using the system, our requirement is always to get high strength signal. Okay, so to obtain high strength signal, if I keep angle of incidence high, if I keep theta I as high, then almost for all the type of materials which I will be using as an interacting material with the optical probe, my quality of signal will be good. Okay, so these two important curves gives us idea that our theta has to be, theta incidence has to be greater than critical value, and at the same point of time it should be having the higher value in order to get a good quality signal strength. Is this point clear? Now, by having this idea, let us try to understand the physical system, how the physical layout of the system of optical probe will be there. So let us consider this is a pipe, and in this pipe my fluid is flowing. So say I have some liquid and these shaded shapes are nothing but my gas bubbles. So these are gas bubbles. Okay, so what I am having, this arrangement is nothing but my optical probe, and this optical probe is having some light source which is connected through the optical fiber cable. So this is a optical fiber. Through this optical fiber it is supplying the incident ray to this particular glass optical probe, and then this glass optical probe will be either having the contact with the gas bubble or it will be either there in the liquid. Is this point clear? So once it is in liquid, there will not be any reflection, and ultimately at the detector I will be getting zero signal. Okay, but when it is present in the gaseous medium, then the bubble is crossed by, sorry, this probe is crossed by the interface of the liquid and gas, which will lead to reflection of the wave, and because of the reflection I will be getting a significant amount of signal at the detector. Is this point clear? So presence of the bubble either in the liquid or gas can give me reflection or no reflection, and corresponding to reflection or no reflection I will be getting either a peak in the signal or signal will be dull. So something like this, stepped variations I will be observing. Whereas the rise is corresponding to presence of the gaseous medium in the path of the probe, and dip in the signal is corresponding to the presence of liquid phase in the path of the probe. Okay, and now what type of probes we can have? First type is conical probe. So here you can see this is a conical probe where this is incident signal. Now it is reflecting, first reflection from this point, second reflection from this point, and then it is moving something like this. Another can be cleaved probe with flat surface at 45 degrees. So this is a cleaved probe where this is incident ray, then it will be reaching this surface. Here we have a mirror, and from this mirror it will be reflecting, it will be reaching here. Here, depending upon gas liquid interface, it will be again reflecting, and my detector signal will be moving in the same path. And this is a U-shaped probe. So in case of U-shaped probe, from here incident signal is coming, then it is moving like this, and then it is moving like this. Now typically the conical, okay, now can you tell me what should be the size of this probe? Sorry? Needle. Yes. So will there be any limitation of size of probe? Can I make it a tube of some centimeters size? Yes. So ultimately, whenever we are using the optical probe, what we are doing? We are putting it within the flow. So it means we are providing some restriction to the path of the fluid which is taking place across the probe. Okay. So if I use a larger size probe, that will be leading to significant amount of variations in the flow. Okay, which will be actually deviating the flow from its natural or usual behavior. So we have to use the probe of size so small that it is not affecting the flow dynamics. So that's why typically the size of this probe is of the order of 10 micrometer or even as small as 1 micrometer. No, so that much strength it is have.
सर एयर बबल फूट सकते हैं ना अगर हम प्रोब अंदर जा रहा है बबल में जब टच करेंगे तो बबल ही बर्स्ट हो गए तो
Bubble will not be bursting. How? I'll show you. Further, we have actually one slide where we'll be showing how bubble will be actually interacting. So it's a very thin one. So if it's a very thin one and it is of hydrophilic nature, so it will mostly try to make contact with the liquid. There will be some film and gap in between the air bubble and the probe. So because of this so small size of this particular particular probe, what we have, there will be manufacturing difficulty of maintaining this precise angle. So that is the reason conical probes are actually very rarely manufactured and used. And this type of flat face, because here we have to only cut a single angle, so this type of cleaved probes are mostly in use. And in the very initial days when cutting of glass was also challenging, then typically this U-type probes were actually in use. It may happen that instead of moving it like this signal can reflect in some other way. Cone is of not interest. The interest is on these angles. this angle and this angle. If these angles are distorted, then signal which is following this path and going through the optical fiber to the detector, instead of going in this way, this can go in this way. And there can be multiple reflections and signal may distort and its strength may decrease significantly. No, because here you have given the round curvature, so mostly the thickness of this curvature is significantly high so that it can take care of this reflection. If you have to cut, but if you have to cast a single piece, then this will be easier. Now you can see the strength, you can see the physical arrangement, how bubble will be actually interacting with the optical probe. So here you can see this is the output signal in voltage and this is our time, and here you can see this is initially bubble which is moving with velocity u and it is coming towards the probe. So initially the value of signal will be low, okay, because it is in contact with the liquid and interface is not coming, so that reflection is not taking place. Then whenever bubble is coming close to the probe, then also we will be finding that there is no perfect contact of the bubble with the probe, because typically we are using a glass probe and glass is nothing but a hydrophilic material. So what will happen in a hydrophilic material? It will try to make most of the contact with the liquid portion only and it will try to repel the gas. So because of this reason, whenever the interface of the bubble we look on the magnified way, this gets deformed, and in between this bubble and in between the bubble interface and the glass surface we have a very thin liquid film. Now you can understand, if your probe is of 1 micrometer or 10 micrometer, then this liquid film can be of the order of few nanometers. Okay, and corresponding to that, you will be finding that your signal, from macroscopic viewpoint, it may appear that bubble is in contact with the probe, but your signal will not be immediately giving you the signal corresponding to the presence of gas bubble. This signal will be gradually increasing to this point, and once the bubble, almost this entire thin film has drained out, then only slowly bubble will be coming in contact with the probe, and corresponding to that we will be getting high signal where when bubble is in contact with air. Okay, and after that again when the bubble is actually leaving, then corresponding to that signal will not be falling in a stepped manner, rather it will be again gradually decreasing. Okay, so I can say that the period from here to here is something which is called as latency period. Corresponding to this itself, my probe should have identified that bubble has reached the probe, but it is giving some delay of delta t1 time in order to give the information that bubble is in contact with the probe. Now, typically, if I use a single cutoff, say this is my cutoff, that if signal strength is less than this, then I will be assuming my liquid is in contact with the probe, and if signal strength is greater than this, then I will be saying that bubble is in contact with the probe. So this type of cutoff value will give large latency period. So this much large latency period will be giving inaccuracies in measurement. To avoid these inaccuracies, what we do, we give the single individual cutoff values for gas bubble as well as for liquid. So we have S2 as the cutoff for liquid. So if signal is greater than S2, I will be saying that now liquid contact is not there. And if signal is less than S1, then I will be saying now gas contact is not there. So these individual cutoffs are just given to avoid the duration of the latency period. Because ultimately, later on this data of the optical probe can also be utilized to measure the velocity of the flow. If I am able to detect that how many number of bubbles are crossing in certain period of time, then it may give us the data of the velocity of the flow as well. Okay, so over here our attempt should be to decrease the latency period to the extent possible. So that's why individual cutoffs S1 and S2 are provided. Okay. So basically when I am using these individual cutoffs, corresponding to that my phase density function of the gas will be becoming something like this. Have you understood? So immediately when S2 is crossed, I have given the phase density function as equal to presence of gas. And when this S1 cutoff is gone, then immediately I have made the signal equal to 0. So this is done to avoid. So if I do these individual cutoffs, so now you can see this much latency period I have actually avoided. And here this much latency period I have avoided. Okay, upon giving the individual cutoffs. Now next comes electrical impedance method. Okay, so in case of electrical impedance method, what we have an inner electrode, then we have some insulation material, and then we have external electrode. So now if I have internal electrode, external electrode, and if I put this into the different fluid mediums, then depending upon the electrical conductivity of the different mediums, current will be flowing from inner electrode to outer electrode. Okay, and the strength of that current flow, that signal can give me the indication that which fluid is in contact with the probe. Is this one clear? So if say gas is in contact with the probe, then it is having low electrical conductivity, so strength of signal will be less. If liquid is in contact, then the strength of the signal will be more and we will be getting more conductivity. Is this one clear? So this type of probe is identical to that of the optical probe we discussed in the previous section. Other than this, we can also have some arrangement like this. This is my first electrode and this is my second electrode. Now in this way, whenever flow will be taking place, depending upon in which portion I am having bubble contact, where I am having liquid contact, the contact resistance in the liquid portion and the gas portion will be different. All of you are clear with this idea, and depending upon that, the portion which is covered by liquid and the portion which will be covered by gas, if we vary the fraction of that portion, our value of output signal will keep on changing. So from this type of probe, because it is arranged in a linear manner and these are placed very close to each other, again we can get the idea of the one-dimensional void fraction. Why one-dimensional void fraction? Because I can measure that, say this much portion is of gas length, this much portion is of liquid length, and then say again this is liquid length. So depending upon the length of the gas portion and the liquid portion, my electrical resistance between the electrodes will be varying, and accordingly my output signal will be actually varying. Is this one clear? So from here we will be getting one-dimensional void fraction. The other way could be, now again these two arrangements were such that these were interfering with the flow. So we can have some arrangement where we do not have any interference with the flow. So in this scenario, what I can do, I can use the stripped electrodes which are just put on the material of the pipe itself. Okay, so in this case, this is my first electrode, this is my second electrode. The contact between these two electrodes will be actually making the electrical conductance different, and accordingly our output signal will be actually changing. Okay, so this type of methods which are based on the principle of electrical conductance of the fluid mediums, these are known as electrical impedance methods. Okay, so we will stop now and we will discuss further in the next class.